So today we're going to be talking about thermal comfort as an alternative energy metric. So using thermal comfort to drive your design rather than energy efficiency. That's the goal with this session. Our learning objectives, we really want to focus on defining the difference between energy efficiency and energy sufficiency, and also giving some feedback on thermal comfort and also giving you tools for modeling thermal comfort in buildings towards the end. We have 3 projects today that we're going to showcase, but before we dive into the projects, we're going to spend a little bit of time defining thermal comfort and defining efficiency and defining sufficiency before we go to the end with the Q&A. So please use the chat box to enter any questions as the presenters are presenting their projects. We'll save them for the end and go through them at the end. So we have joining us today Tommaso Bitossi, who is the Associate Director at Transsolar KlimaEngineering, and Apoorv Goyal, who if you've attended our sessions before, actually Tommaso and Apoorv have all of the presenters have joined us before. But Apoorv is also the chair of AIA COTE New York. And he's an associate at Elementa Engineering. And then lastly, we have Kit Ellsworth, who is joining us from Kieran Timberlake, where he's a building performance specialist, and where he works to support occupant comfort, energy efficiency, and carbon accounting in building design. So what is thermal comfort? Thermal discomfort, more likely, is, we're always trying to find a level of satisfaction. And I guess one of the things we're going to kind of look at is this what comfort looks like? ASHRAE 55, which is what most of us are probably most familiar with, defines thermal comfort as the condition of mind that expresses satisfaction with the thermal environment and is assessed by subjective evaluation. I think I want to highlight that this is a subjective evaluation and measurement criteria. So predicted mean vote, or PMV, is the first method that ASHRAE 55 goes into. And it has 4 environmental factors and 2 human factors that are used to calculate whether or not a person is comfortable. I'm not going to go into too much detail because our project examples are going to dive into each of these metrics in a little bit more detail. But predicted mean vote is usually paired with predicted percent dissatisfied, or PPD, where this is where the subjectivity comes in, because it is a survey that is done to assess, given the conditions of air temperature, relative humidity, etc., how comfortable are people saying they are, and then that's used to assess whether or not the space is comfortable. But when we look at those 6 metrics, there's actually far more factors that affect those 6 metrics that we need to kind of be aware of. And so this slide is meant to expand our understanding of those 6 metrics, which is airspeed, air temperature, humidity, mean radiant temperature, and then the human factors of metabolic rate and clothing value. There was a paper published recently, last February, that talks about lessons learned over the last 20 years of the CBE occupant survey. In that survey, temperature and sound privacy were found to be the least satisfied. People were the least satisfied with those 2 metrics in the last 20 years of doing the occupant survey. So that says something. Our buildings are not comfortable, and we're using a lot of energy to make them more comfortable. So what can we do about that, and how can we approach design differently to address that, right? And then to further expand that definition, there are even more factors, right? If you consider all of the different factors that this chart is an expanded version of this chart, where it's looking at, okay, you've got these 6 values that ASHRAE 55 looks at, which are influenced by all of these other factors. And then there's even more, like the building wasn't part of the earlier slide. So there's just so many factors that contribute to thermal comfort that you really have to expand what you're thinking about, how you're thinking about thermal comfort and its relationship to energy. So there's also the adaptive comfort model that ASHRAE goes into, and this is where you are looking more at outdoor temperature, and it has a wider range of temperatures that is acceptable than can be explained by the PMV model. So one of the projects we're going to see today is going to be focused on two of the projects are going to focus on adaptive comfort and using natural ventilation. With that, we're going to do a little segue here to talk about efficiency versus sufficiency. And we're going to use cookies as an example, just because it's Monday evening. So we don't want to talk about numbers, and we want to keep it a little interesting. So in the late 70s, the US embarked on an Eat Less Fat campaign around the same time that it embarked on a Use Less Energy campaign. So fat was a villain, and we were convinced into switching to reduced fat food as the healthier alternative. But by the late 90s and early 2000s, studies were showing that an exponential rise in obesity-related illnesses, right? So it wasn't really working. And if we look at it, the serving size stays the same. The calorie count doesn't change by much, and the sugar content also stays the same. So, and because it's healthier, you might actually end up eating more. So is a reduced fat Chips Ahoy cookie really healthier than an original? What really changed? What does this have to do with energy efficiency? Well, that's because we see the same thing with energy. In the 70s, when the Energy Policy and Conservation Act was signed, it was meant to make our buildings more efficient, but in fact, it didn't. We started using more and more energy, even though we were, our buildings and systems were become designed more efficient. So the reason for this is researchers have labeled this effect as the rebound effect. There's still significant ambiguity on how to define, measure, and characterize the uncertainty resulting in the rebound effect. The author of the paper that this diagram came from states that if energy efficiency strategies save money for a consumer, the energy services become cheaper relative to other goods and services. So the consumer may purchase more energy services. Seeing an increase in your net income allows you to spend more money on energy services or on other goods and services, which then in turn require more energy to be produced. So over the past 3 decades or so, energy modelers, energy economists, and policymakers have long debated over the magnitude of the rebound effect. But while they've debated on that, one thing that has been certain is that energy efficiency measures are eroded due to consumer behavior, right? We save money or energy, so we take it as a license to spend more, use more, or in the case of the cookies, eat more. That's where the concept of sufficiency replacing efficiency can start making some real change. Sufficiency is pretty straightforward. The idea, it's simple, that there's something like too much, or there can be just enough. And the idea for this session is to focus on how can we make our buildings sufficient. And so just going back to the cookie really quick before we move on to the project presentations, sufficiency would really be changing the service size and keeping the original, or going to reduce fat and still reducing the serving size. And that's a human behavior intervention. And that's exactly what we need in our buildings to make them more energy efficient. And we can do that by using thermal comfort, because trying to convince someone to use, one fewer device, I don't think is going to really cut it. But that's why we're pairing the idea of sufficiency with thermal comfort, because it really can help. So how can we expand our definition of thermal comfort using sufficiency as a driver? We have 3 projects. And so we're going to start first, we're going to look at a recreational facility, which is located in Climate Zone 5A. It is a gym space, and the reference standard being used is ASHRAE 55. And the strategy there is to use air movement as a key element to provide thermal comfort while also expanding the definition of comfort. And they're investigating how do interior set points and thermal comfort expectations drive the size of a mechanical system. The next project is going to be a scientific research facility located in Climate Zone 6, also using ASHRAE 55 adaptive comfort as the reference standard. It is a office/retreat/research center, and they're investigating there, first looking at outdoor comfort and seeing what impact that has on program and occupancy, as well as system design. And lastly, we have a mechanical engineering school located in Climate Zone 5A. This project is unique in that it's not really looking at any of the standards. They're using design and thermal comfort mapping spatially within a space to understand how window to wall ratio, sill depth, and window placement can prevent discomfort, and what strategies minimize downdraft and radiant discomfort at a window. So it's a very precise investigation. And I'm just really excited to listen to these presentations. So I'm going to stop sharing. So our first presenter can share their screen. One second.
All right.
So Tommaso is going to be our first presenter.
Can you see my screen?
Yeah.
In presentation mode. Right. Thank you so much for having me today, first of all. And we are talking now about comfort, of course, as it has been said, but for a gym, which was something pretty new for me as well, because recreational centers and gyms, you know, they are not so, it doesn't happen so often, at least for the projects I had in the past to have one. We are in Princeton and Princeton University. I can't talk too much about this project. I can't show too many visuals about it, but again, it's the actual and current gym, Dillon gym, and you see it from the top and one view from the street level. It is about the extension of the gym and the partial renovation. So the first step was to maximize the renovation in a way that we could keep under control the embodied carbon. So we wanted to reduce embodied carbon. And the other part was, of course, to extend it, because Princeton is seeing a growth in population and students. And so the actual and current facility was not big enough. So you see here where we are working on, which is the southern extreme of the gym, everything except for where you read cardio to the bottom right, that is the extension, and all the rest is the renovation. So mostly it is the renovation of a space, and then there is that little extension for the gym. And this is level number, we call it level C, which is basically the below, kind of below grade, in between below grade. It's a kind of a hilly landscape. Now, and this is why I said it doesn't happen that often, because now suddenly the definition of ASHRAE, which is still correct, it works with much higher metabolic rates. So I do already a step back. That this is what you see here is the overall and holistic definition of comfort. It's air temperature, but not only air temperature. It is mean relative temperature together with air temperature. It is relative humidity. It is airspeed. And then it is also what you are doing inside the space. Are you running like the lady on the treadmill here? Are you sitting? Are you working on a desk, etc., etc.? This has a big impact on the overall comfort within a space. And then it is also how are you dressed? So when we think to a gym, you are usually in a very summerly clothing factor. That's the way it is, which is more or less 0.3, 0.5, depending on how you're dressed. And this is positive because you are usually underdressed, but you are running or you are lifting weights, and this boosts up your metabolic rate. So suddenly you feel much warmer than just typing on a keyboard. And all these pieces here are very important to define comfort within a gym. I have to say that ASHRAE, with these metabolic rates for a gym, it is out of the jurisdiction. So metabolic rates are too high. So ASHRAE actually doesn't comply with these metabolic rates. But still, the definition and the calculation and the equations behind the definition of thermal comfort in terms of predicted mean value, it is still valid within, I don't remember the range, but it's up to 4 metabolic rate, which is what we studied. Going back to sufficiency, the first very, how can I say, provocative message to Princeton University was, wait a second, do you really need a building? So the architects look at me like, what is this guy talking about? We have been hired to build a building, and this guy comes to Princeton and says, maybe we don't need a building at all. But the point was, again, about sufficiency. So if you look at this kind of visualization, you see there is temperature on top. I forgot to mention the architects, by the way, MJMA and Dixo together. Apologies for that. So you see here a visualization of thermal comfort in terms of temperature and in terms of metabolic rates. Metabolic rates which can go from metabolic rate number 1, which is you typing, up to metabolic rate number 4, which is you playing tennis. Of course, if you play tennis, you have air movement because you run, so you have a higher metabolic rate, but you also have much more air. And this means that if you bring it back into temperature, you can be kind of comfortable within different temperatures. So we said, what if we just go outside in the climate of Princeton without a building? For how much time of the year can you do this activity without a building? So you can type on a laptop, so office work, for 18% of the year. But for example, you can do heavy lifting for 38% of the year because your metabolic rate is higher. So even if it's slightly chiller, it's actually fine because your body actually benefits of that chill air around you. If you play tennis, you can do it for 34% of the year without any building. So there is where we started. And then the other big point, which was more philosophical in a way and goes back to sufficiency, is, for example, do you really need a treadmill in a gym? And first of all, if you need one, do you really need an electrical one? There are self-powered treadmills which has no power, 0 horsepower. If you have an electrical one, it's 4 horsepower. So what's the point of running on something which requires electricity to work? I mean, it doesn't make sense, right? And then, do you actually need one? Maybe you design your building and this has a huge impact on the way you program the building and you develop the massing and the floor, etc. Maybe your corridors are actually places where you can run, and then you don't need a treadmill. So this was a bit the idea and the concept behind this gym of really try, you client, we are here to try to trigger your imagination and to kind of support you in answering the question, what do you really need for this building? Before telling us what you need, let's start playing with all these variables. And then the key point, do you really need to keep the building at 72 Fahrenheit? Now, I'm European, as you can hear from my accent, I'm Italian. I have been working in Germany where this idea of sufficiency, it's very important. And we usually do not overcool the buildings in summer, as I experience in US. And I live in New York now, and I was shocked. I moved here in summer where subways were at 68 Fahrenheit. And I was like, give me a break, guys. Outside is 80 Fahrenheit. I'm dying here. And the shops are the same, etc., etc. And also this number came to us, 72 Fahrenheit, 68 Fahrenheit, depend in summer for a gym. So we went through the regulations. There is no actual regulations. There is the International Fitness Association, and they basically say, we can't tell you what to do. Just do everything in your power in order not to have complaints from your users. And we know users they mostly complain for everything. But and this is what they are saying. And so the building facility managers or whoever is operating the building, usually they say, if I keep you at 70 Fahrenheit, at least you cannot argue that it's too hot. And that is the most of the argumentations that we hear when buildings become so overcooled in summer, right? So what we said is forget air temperature, first of all. Air temperature is not comfort. You imagine you are in a car, your air conditioner is boosted at 60 Fahrenheit, but you step in, you have the dashboard, which is super hot, you do not feel comfortable. Even if your air temperature is at 60 Fahrenheit and you are sitting doing nothing, everything is so hot around you that you do not feel comfortable. So forget the notion of air temperature as a measure of comfort. And let's see all the references that you are thinking in. So the first one, for example, the International Fitness Association, they are talking about air temperature and relative humidity. And we said, this is not enough. You cannot reference to these associations which are not having a holistic understanding of thermal comfort. Otherwise, you will oversize your mechanical systems. You will pay much more money. You will end up overcooling your people inside. It's going to be just not the right success metric that you have to follow. And if we go down to the other matrices, then we go to ASHRAE, which, as we said at the beginning, considers everything, air temperature, relative humidity, mean relative temperature, which is, in a few words, the quality of your envelope. Very important, the quality of your envelope. Airspeed, metabolic level, clothing factor. And then you see suddenly how ASHRAE can relax up to 78 Fahrenheit if you have air movement, ceiling fans. See, if you have elevated airspeed, that's the right way ASHRAE defines it, which is a totally different animal than talking about 72 Fahrenheit or even 68 Fahrenheit, right? Now, the mean relative temperature, the quality of your envelope, very important. Often you talk with users, you talk with building facility managers who are used to old buildings, to very poor envelopes, no shading, no insulation, no thermal mass. This means that you are in a car. You control air temperature, but you do not control all the rest. And you see in this sketch, let's imagine International Fitness Association as guideline. Your air temperature, which is the second line, is a 68 Fahrenheit. So exactly what they are recommending you to do in between the lines if you read. Your roof temperature is 100 Fahrenheit, is light. There is no thermal mass. There is no insulation. Your relative humidity is 65%. And then you imagine either you do stretching or you do heavy lifting 100 pounds. According to ASHRAE, and your point is, your red point is where you are, the blue comfort area is where you want to be. So when the red dot is inside the cyan area, this means that it's comfortable. Those conditions are actually comfortable. So the International Fitness Association says, yes, this is what you have to do. But this is a new building. In a new building, the envelope is a good envelope because we are targeting passive performance first. That's the very first step, insulation, thermal mass, shading. That's the very first step. And then suddenly, if you take into account the overall picture, where your mean relative temperature goes close to the air temperature, so like 78 or 80 Fahrenheit, depending. So you have insulation, maybe you have a green roof, so you have thermal mass, you have exterior shading, then suddenly 68 Fahrenheit air temperature is too cold, even if you are heavy lifting. So we said, if you have 78 Fahrenheit and you have air movement, very important, so elevated airspeed, you can keep your air temperature, since your mean relative temperature is around 78 Fahrenheit as well, keep it at 78 Fahrenheit. And you will reach still comfort. This is a gym. I struggle with the idea of comfort. I called it thermal experience, in a way that you can do your exercises sweating a bit because you are in gym, so that is fun, that is fine, but still in a healthy environment in a way, right? You can't have a heat stroke at the end. So that is the target. I don't know if it's comfortable when you do heavy lifting, but that was the target. And then we built a narrative around it, right? There is lots of communication when you talk about this. Your client, the users, they need to understand. We said, this is what you measured in your current gym. This is even air temperature. So it's not operative temperature, which is tough to measure, it's air temperature. Your building is so poor, your envelope, the way you cool it in this specific room, they had no cooling, that you go up to 90 Fahrenheit. Of course, you have complaints from your users. But this is what we simulated. With the simulation, we are doing now a holistic understanding of comfort. Every dot here in this carpet is 1 hour of the year. You see January, February, March, so all the months, and on the y-axis, the day, so from midnight to midnight, basically, and the red dot is a critical hour, where critical hour is when actually you have 78 Fahrenheit, because that's the other point. We size the mechanical system for 78 Fahrenheit, but how many hours of the year you actually have 78 Fahrenheit, which is still comfortable, but more on the high end of the system, 3% of the year, only 3% of the year. So is it sufficient to design a 78 Fahrenheit, which is maybe a bit stretched, but still comfortable for 3% of the year? This is what we asked to the client. And then we said, look also when this happens. These usually happen in the morning because of sun position, where usually your gym is empty because you have students in the afternoon. So it's actually 0% that happen when you have people inside, your students, but otherwise it's 3% if you consider it in the morning when usually it's empty. So that is the narrative we built, and we said, why do you want to do it? Because not only people are more comfortable, but also because you can bring down 20, 50% energy cost and carbon emissions. That is the other reasons why we wanted to do it. So I stop here. And I'm very happy to answer questions. And I remind you that, if you go to the gym, maybe you want to run to the gym instead of driving to the gym, also in the name of sufficiency. Thank you.
Thank you, Tommaso. That was a great presentation. We are going to save the questions to the end. So if you want to post them in the chat box, go ahead, while our next presenter, Apoorv Goyal, shares his screen. And
yes. Okay, do you see my screen in the presentation mode now?
Yes.
Perfect. Okay, so thanks so much. So that was actually very, very good presentation, and gives me a lot of background, in fact, which I conveniently skipped in my presentation about thermal comfort and defining, the adaptive comfort and everything. And it's kind of the project I'm going to talk about is almost in a very, not a similar setting, but talking about the similar things about sufficiency and efficiency. And it's a retreat center in Toronto, and to be honest, we had a very good client and MSA architects in Toronto. It was a great team because we started off with this with an amazing goal of can we design a net zero energy, net zero carbon building, and go all in terms of how we can reduce our energy use. We need to maximize thermal comfort in whatever format we have to. It's a building where researchers from the University of Toronto are coming in, spending a couple of weeks, doing research outdoors. So it's middle of it's on top of a hill, forested land kind of a thing, and this building is pretty much the only structure that exists out there in that surrounding, at least. So when we started, of course, looking at the energy efficiency measures and making sure that it's a low energy consumption building. One of the goals that we started to discuss and put it in front of the client was, can we in fact because it's a climate 6A, we don't have a lot of summer times, and I'll go through the climate in a second, but is it even possible to think of this building without any active cooling systems? And that was a goal that, that kind of drove the design, the process, and the project going forward, still in design. But the client were excited about it. And so we did have very interesting and meaningful conversations about what does that really mean in terms of system design, but also what does it mean for the researchers that are coming in? How does that shape the use of the building, time of the use, and all those things? And based on that, essentially, of course, natural ventilation becomes a really, really important part of this of the design process, but also looking at other passive strategies wherever we could to try and at least eliminate active cooling. Now, I'll break the news now. We do have active cooling still in the building just for emergency purposes, but the whole design does focus on minimizing that. So, very beginning, just to even get started, and again, you saw that rendering. It's a very small building, so it's a cold climate, of course, Toronto. And we're talking about a very narrow, very short summertime, and the way we define summertime is basically prevailing outdoor temperatures on a running mean. When it goes beyond 15 degrees, again, sorry about the metrics. It's approximately, I think, about 72-ish, I think. But then you can see the higher average goes to all the way to 77 and drops down to even 64.5 during the night. So there's a good diurnal shift. We from the beginning, we knew we have to incorporate thermal mass and whatever strategies we can to minimize the swings and heat buildup inside the building so that we can very quickly flush it out and have the entire building comfortable. The other thing that we started talking again from the thermal comfort perspective was the adaptive comfort. And just defining what thermal comfort for this purpose really means. So you saw one version of the PMV and the PPD in the presentation, the graph. This is again ASHRAE 55 defining how adaptive comfort works. The idea being that depending on what the outdoor temperature is, you will be comfortable in a higher temperature indoor rather than or you can still feel comfortable in a higher temperature rather than a straight 72 degrees set temperature or whatever. And then additionally, you can start increasing that thermal band or thermal comfort conditions using ceiling fans and elevated airspeed, as Tommaso also mentioned right now. And then the light blue bands are basically the difference between if you are designing for 20% people dissatisfied or 10% people dissatisfied. So it's just a wider range of how much how many people you are actually 20% has been always a range which has been acceptable. So just looking at this and having our conversations with the client and with the architects really helped us to communicate what we are trying to achieve and what that would mean for the design process. This is again before even we started the schematic design, so it started to inform things like what kind of form we need to have for natural ventilation, and we'll probably have operable windows separated by a vertical separation and things like those. So, just starting to get some guidelines out there for the design team as well. Again, very important to have these conversations as soon as possible after setting a strict goal about thermal comfort, about low energy, low carbon, whatever. But having these discussions early on helps to drive the process and the design in that certain way. And so from there, basically starting to understand what the design approach really should be, getting into more detailed discussions, tackling things which are easier and low hanging fruits. From the onset, of course, for every building, irrespective of you're designing for thermal comfort or not, for system size and for peak loads and everything, you start to look at minimizing the heat gains. You design your solar control in a way where you don't have unnecessary hours when the south or the west facades are exposed to the sunlight. And you will need the system to take care of those loads. So just reducing those, including thermal mass, to really shift the peak times, and then start to thinking again for this purpose, because we knew it's going to be a naturally ventilated building. We could think about putting in thermal mass and thinking about night flush ventilation, for example, to just offset those times when the heat builds up in those times. Thinking about natural ventilation in a lot more detail about what kind of spaces we have, what kind of, when are these spaces being really used, what are some of the design approaches that the architects were thinking about, and how do we start to tie all these things together and come up with a strategy for the building, for each space, including, you have to start looking at what the window sizes would be, how much of these windows are opening to maintain, to get the airflow, what are those orientations where we want the windows to open, where we don't want those windows to open. Start talking about operation and controls, because that's when, client role becomes really, really important. That if you're opening windows, there's certain amount of infrastructure, there's some certain amount of hardware that goes into it, but also putting across that point that in general, if occupants have that amount of control, you can control the windows. It's more of a perception. Thermal comfort is a perception as well. I mean, that's where the PMV and PPD and everything comes in, right? It's a vote. It's how you perceive your thermal environment. And so, having that conversation that if we do have operable windows, if we have control, and people are in a casual setting, there is a higher chance that even with a higher temperature, they will, the occupants will feel comfortable and not necessarily go in and switch on cooling, for example. And then once we exhaust all of those, then also in the end, again, the idea is to minimize active cooling as much as possible. So what are some of those other strategies, passive strategies, earth tubes and labyrinth, and can we just put in a ceiling fan and get, do with that in terms of and not switching on the active cooling at all. So just going through those approaches and having a very meaningful conversation about what the design should be, which starts to got us into, understanding, again, going more into details about what the natural ventilation. So very small building, just one floor. In fact, there's a basement, which is mostly mechanical space or storage space rather, which is, again, an interesting story. I'll come to that in a second. But primarily three broad use types in the buildings: the zone A, which is the southmost zone. So north is vertically up. Zone A, which is more of a hall kind of a situation with a small kitchenette in there, so this building is designed for like about 30 to 40 occupants at any given point of time. And this hall kind of provided the occupants for a space where they can gather after they come back from the research throughout the day, just, come in at 5 o'clock or 6 o'clock, or even stay in during the daytime, and really spend time, socializing or talking and presentations and whatnot. Zone B, which is more of a bedroom situation. So it's a place where about 20 people can spend the night. So that zone was always designed, or has been designed to serve only only during the nighttime. And then the zone C, which is a small classroom space, which is just, for the researchers, for presentations and in classroom educational purposes. So these were the main areas that we were focusing on in terms of providing a system. or heating and active cooling system. And based on this is in parallel with how the architecture design was progressing. So just kind of coming up with the right scenario and right ventilation design, working with the architects that the hall needs to be a double height space. So can we have a stack ventilation, which means we need some windows up on the top, and then we can also have cross ventilation throughout. There's a courtyard space which potentially during the summers will be shaded because of trees and mutual self shading. So you can pull in a lot of cool air from there. Similarly, how does the bedrooms work? So again, putting in a nook there or a ceiling nook kind of a thing with some bunk beds in there so that you have air moving through the bed and the occupants really be feeling comfortable around there. And then the third type of space, which is the classrooms, where we're just basically talking about a single-sided single-sided ventilation, essentially with windows vertically separated. So I'll focus on primarily A and B in this presentation. C was a little tricky. The depth of the room was not very ideal. We do have natural ventilation going in there, but I think A and B are much more interesting. So when we talk about the hall, right, in terms of how it relates to design and how effective the system is, we started doing some sensitivity analysis very early on to understand what is the opening and the inlet and the opening area that we are talking about for the building, which means what's the area that you need for the cool air to come in and move on through the stack vertically and exit out from the exhaust windows, and what is that area as well. So looking at the sensitivity and the dotted lines is different heights between the top window and the exhaust windows and the inlet windows. Kind of 7 to 8% or 7 to 9% is where the curve starts to get flattened out, which is inexperience as well. It's a very common number that we see most of the times, which means you're talking about 4% of the window area or 4% of the floor area, which should be operable in the windows. It's a little bit of a confusing metric, but that's how the whole thing is adjusted, which also gives you about 11 to 13 and a half, 14 air changes, which is pretty high. But also for a space like this, it's great to have all that air flush out the space as soon as possible, as quickly as possible. And at the same time, you don't want a lot of air movement that it's that the elevated airspeed itself becomes uncomfortable, not just because of the draft and the temperature purposes, but also practical purposes, papers flying around and all sorts of other issues. So trying to optimize those things and making sure that the design team had good idea about what they're designing to. And then, so that's where the adaptive comfort comes in, and to communicate this whole thing to the client, because the client, of course, is very, they're very concerned about these are researchers. They need to feel very, very comfortable. You cannot just say that, hey, it's going to be, whatever, 80 degrees and it's fine for a few hours. Although we did have a conversation where, there was an idea floated that if it is 80 degrees inside for a few hours, they can always go into the basement and or go out and study and whatnot. But for all practical reasons, it's something that we need to discuss more properly. So plotting whatever, doing a simulation based on what the design is, what the materials are, and without any active systems, you see how the yellow dots are basically everything that is depending on the outdoor temperature, you fall within the adaptive comfort zone. And then few other hours that adding a ceiling fan or elevating the airspeed also gets you in within the comfortable zone. But then there were still about 160 daytime hours that were yet still uncomfortable. And again, as I said, right, the hall was being used in the daytime, so we filtered out the daytime hours only. And so it's 24 nighttime hours, which we didn't really, it's not a big deal to think about, but 160 daytime hours were definitely a big time or a lot of time. And then plotting it on a heat map kind of a situation, just to understand when exactly these hours are going to be uncomfortable, and does that work with the schedule of the researchers and with the university, and can we think about where or how we can mitigate that some other additional hours could be we could ignore those hours almost in a way. But before we get into that discussion, right, rather start looking into other strategies. This one is just with, if we introduce earth tubes for pre-cooling the air. So before you have your natural ventilation going in, but we are also feeding in some cool air using the earth tubes. And what does that? How does that elevate? So you can see it's a huge difference, especially in the shoulder months when it's still relatively cool outside. You can relieve some of those hours as well, which really sat well with the client, with the design team. We do have earth tubes in the building now, or as part of the design now. So that definitely was one of the exciting things. The earth tube also proved very, very helpful in the classroom situations where we could not necessarily ventilate the entire room only with window ventilation. So on one side of the room, we could add earth tube pre-cooling air. And then moving into the bedroom situation. So again, similar thing, but a little bit of a different thing, different way to think about it now, because two things happening. One, the room is being used only during the night. So it's a better situation because we do have fewer hours which go really, really warm. But there's a big difference in terms of how these spaces are used, right? So hall, it's more of a casual setting. So we had a little bit more flexibility in terms of comfort and option for people, even if it's a couple of degrees higher. It's not that big of a deal. Versus in a bedroom where people are sleeping and you need a good night's sleep for to be fresh for the research next morning or whatever. Plus, people are or the occupants are really, really close to the window. So there are security issues. There's all sorts of other things happening where we had to be very, very careful about how these windows are being opened, what kind of windows are we able to use, and how much of the wind movement is going to affect the occupants again. So on the right, again, similar metric or similar sensitivity, similar numbers that we achieved, again, between 6 to 8% of the open area, 11 to 12 changes per hour. So that's again a good number that we thought was to flush out the heat buildup in the room. But really going deeper into that, and it was only about 24 to 32 hours during the nighttime, and specifically during 1 week when we were really concerned about the specific July week. And the idea was, it should not be that the temperatures are uncomfortable for consecutive 2 or 3 nights or whatever, because then that becomes a problem, which kind of also was the case, which is where we started, kind of diving deep into what exactly that specific week means. And so plotting hourly temperatures, gray lines is the outdoor air temperature, and blue is the indoor operative temperature, including again all the materials, all the thermal mass and loads and everything. And you can see that it's still within that adaptive comfort range, but you do have certain hours when there might be a little bit of a problem starting to happen without ceiling fans, or the temperatures going much higher or even a little bit higher than these temperatures. There were a couple of times when we started noticing those hours which were getting uncomfortable. The other important discussion around this was all of these simulations are being done using a TMY file, whereas actual weather, it might be completely different, or it varies a lot, and we might in fact have a lot of higher temperatures during the night. We might have a week where it's a heat spell or whatever, and those were the times where it became really important to consider what we need to do in terms of providing comfort, which is the reason why we do have active cooling in the building. But the idea is that the cooling only switches on only during the extreme conditions where the temperature goes above 82 or 83 degrees outdoor, and people are really uncomfortable. One of the things I forgot to mention, the whole net zero story, it's kind of connected, because Toronto, certain jurisdictions, you cannot necessarily send back all the electricity that you can send back the electricity that you generate, but anything excess that you're generating, it's a problem, because it's a hydroelectric system. So there's a lot of things. So we wanted, even if there is a system sitting there that can accommodate those extreme heat hours, it's not necessarily running each year and creating that problem of generating excess energy, or extracting, or drawing excess energy from the grid and not being able to match the difference and things like those. So just a shot for the hall itself. You have low windows on both the sides. You have higher stack windows within these slats, which I think is a pretty clever design. We had good solar control so that we can we're not building up heat anywhere. In fact, these windows also help in a way to kind of increase the temperature on the top and making the stack ventilation be much more effective during hours. So it's again an all-rounded approach to design. So that was me. Stop sharing.
Thank you, Apoorv. That was amazing. So it was really great to see how you were using that outdoor comfort to dictate indoor thermal comfort. So our next presenter is going to be Kit, who is going to present mechanical engineering building. I'll let him introduce the project and share his screen.
All right, thank you.
So if you guys have any questions while he's setting up, please do add them to the chat box. We'll leave some time at the end for questions.
How does that look, John? Can you just look good?
It looks good. Great.
All right, let's jump into it. So very quick background. My name is Kit Ellsworth. I'm a member of the research group in Kieran Timberlake. If you don't know COTE, we're a medium-sized architecture office in Philadelphia. We don't just make buildings, we make tools, both physical and digital, which allows us to gain some insights into how buildings perform. And my role within the research group is a building performance specialist. So I'm helping bring to light the kind of occupant satisfaction and energy side of buildings performance and help architecture teams address those early in design. So for this project, this is a new mechanical engineering building for Carnegie Mellon University in Pittsburgh. This is a complete, it was the demolition of the existing SCAFE hall and a rebuild. So the new building includes labs, classrooms, faculty offices. As you can see in this rendering, it's under construction right now. So in this rendering, there's kind of 3 distinct masses. Each one of those roughly corresponds to a different program type. So if we just take a slice through the second floor, We can see generally the kind of the south mass is faculty offices, classrooms are grouped into that northern bar, and the kind of lower podium that was shown on that other rendering is mostly the labs. So for this case study, we were examining something that should affect all projects in cold climates. We were focusing on mostly reducing the HVAC system sizing or trying to eliminate them completely. We did this through building a framework of envelope constructs or rules that allowed us to work with our engineers to understand kind of like what fenestration designs allowed us to minimize or eliminate systems both on the heating and in the cooling side. And for this case study, I'm just going to talk about the heating side and a study that we looked at in the faculty offices, so those little green bars there. And in this, our mission was to eliminate the perimeter heating in those faculty offices. Why? Because it's extra heating, it's extra equipment, first cost, takes up floor area in those offices. And we know through smart design, we can essentially eliminate the need of those. So when we were in early design, we were talking with our engineers and asking them, what is it that causes that? Why do we need these perimeter radiant systems? What is it that is necessitating these extra heating systems at the perimeter? Because we know we're intelligent, we're focused on human comfort and energy saving. So how can we actually remove these systems? So in these discussions, we learned that these perimeter radiant systems are in place to help combat two passively triggered effects of cold facades, and those are radiant discomfort and downdraft heat loss. Downdraft discomfort, I'm sorry. So I think through this last hour or so, we've heard a lot about mean radiant temperature and radiant heat loss. So I'll quickly kind of do an overview of that. MRT, or mean radiant temperature, is a factor of surface temperature, but also the proportion of different surfaces within your view. So if you're standing in a space and you kind of cast out a 360-degree sphere and you're kind of seeing all these different objects that, if you were to shoot out little rays from your body that you'd run into. And your MRT is a factor of maybe how close you are to certain objects, the surface temperature of those, some thermal surface like material properties. So in this example, you can see this little person placed in this small office. He has, it's a 6-sided object. There's also a window in there. So his MRT is going to be, dictated by his, relationship to all those surfaces. In this case, we're looking at the window and how cold that window might be. So in this case study, we're trying to find how can we eliminate perimeter systems? How can we design so MRT is not an issue? So we fix all those other environmental and personal factors that we learned about in the PMV and PPD thermal comfort models. So indoor air temperature, relative humidity, air velocity, clothing, and metabolic rate are all fixed. And through that, we can decide what the minimum MRT value must be to maintain comfort. So when we go through these design studies and we try and simulate MRT, we're trying to find designs that keep MRT values above 66 degrees Fahrenheit throughout the floor plate. On the other side is downdraft discomfort, and this may be a term that not everyone is familiar with. It's a little bit not as common as MRT or some of the other thermal comfort issues. It's more of a localized thermal discomfort, and this is only a factor at facades because downdraft discomfort is a product of very cold windows or cold exterior surfaces, and it causes this this air loop in the room where airflow right along the glass becomes cold. Colder air is more dense than warm air, so it starts to fall and it gains momentum by the time it hits the ground or the floor, cascades and plunges across the floor plan, and usually causes a draft sensation across people's ankles. So it's downdraft because it's falling down from the window, and it's causing discomfort only in the winter, only in cold facades. So through a very similar approach to the MRT in terms of finding what the limits might be for downdraft, we fixed the other kind of values and found the threshold for downdraft given those other factors to be 0.11 meters per second. And for reference, this is a very low airspeed. This is typically what engineers would assume is a background air velocity for a room. So this on top of that background velocity may be like a gentle breeze going across your ankles, very gentle. So it's not much. So in order to do this, we used Honeybee Legacy, the old version, through Rhino and Grasshopper to do these simulations. And we did a pretty lengthy deep dive and literature review into the downdraft calculations and the papers that they're based off of. I'll spare you all of the details, but I just wanted to call out kind of two important elements. So if you are, grasshopper literate and you know ladybug and honeybee and you feel ambitious, you can go and do this on your own, but I'd say not without guidance from your engineers and not without these two things in mind. So the honeybee default equations do not account for kind of horizontal protrusions, sills, mullions that may break up the downdraft coming down the window, and they don't factor in terms of internal heat gains that may be more representative of a program such as an office. So what I mean by this is on the left side, you have a simple line sketch of the downdraft. So this helps maybe imagine what downdraft is, because we'll never actually see it without any kind of like smoke or tracing gas to highlight how the air is moving. But at the very top of that diagram, you could see warm air from the top of the room meets that cold plane, that cold air right on the air film of the glass, starts to plunge down, more arrows indicate more momentum, and it hits the ground and flows across the floor. If you were to introduce a windowsill or kind of very purposely designed and included kind of horizontal interior mullions, you could see it'll effectively break that downdraft effect. It'll kind of launch the air into the space, and kind of each little vertical span creates a new downdraft. So it's a great way to help try and combat this. There are studies, I included a link here, a citation where you can see the effect of those. And on the right side, the internal heat gain, this is the paper that Honeybee bases its equations off of. It's a CFD paper, it's computational fluid dynamics, where they're simulating airflow in a room. And they start off with an empty room and a cold 100% wind to wall ratio exterior surface, which is highlighted in blue. They have no internal heat gain, so it's just relying on natural loops here. And as you add heat gain into the space, that top part of the room gets warmer, and it creates a kind of a greater loop, and downdraft speeds get it faster when you add more internal heat gains. So the one that Honeybee uses is this extreme here on the very bottom. They are pretty much assuming that your heat gains are equivalent of a laboratory setting. So if you have a situation like we have here as in an office, it's going to be over predicting downdraft based on whatever designs you're feeding into it, which has positive and negatives, and we'll discuss those at the very end. So just a kind of a word of caution in terms of approaching this as a black box. I think it's very good, and I'll advise this kind of whenever you go exploring into programs or simulation programs, just always understand what is actually running in the background. All right, so enough of under the hood look at downdraft, and let's get into kind of what is the impact. Why we're obsessed with targeting perimeter radiant heating, I kind of mentioned at the beginning, and I'll just also apologize for using this building as an example. It's not one of our own, but it's one of actually like my favorite buildings around Philly. It's right on 38th and Baltimore area. I love kind of the external screen here, but I also found these images because it shows us what perimeter radiant heating looks like, and most times we may not even notice it. I think it's done so well, it's very sleek, it's integrated into the whole window system, but you can see right on the bottom, you see the vents, and there's hydronic radiant tubing enclosed in that. And I think it's just done very well, but architects, I think, often relegate these services to engineers, where we can also take back some of this responsibility that will eliminate these systems, which saves us cost. It'll reduce our annual operating energy and operating cost. But also in thinking about this as a kind of a larger carbon picture, that's a lot of maybe copper or whatever the material might be, tubing that's running through the building, that's adding embodied carbon to this project. And if we were able to get rid of this, we can gain back a little bit of area, and that goes a long way in enclosed private offices as well. So that's kind of our mission and kind of the larger trade-offs of this perimeter radiant system. So if we're really concerned about thermal comfort in this case, our kind of mission is to find the best window design that reduces or eliminates the need for that heating through the lens of MRT and downdraft discomfort. So the way we set up our study is we took our typical office dimensions here, and we looked at what combinations of justification, left to right movement, aspect ratios, window area result in the lowest MRTs and downdrafts. So as an example here, we have those 3 columns for the 2 different criteria, and we tested out, I think 4 to 5 different iterations or increments of each of those. And just as some quick examples, you can see we end up with kind of square windows, vertical strips, ribbon windows, and through all those different permutations, we get around 2,000 different simulation. So if you look closely, you can see how those window designs change in each one of these image cells. But there's also 3 different false color grids here, and I'll explain what those are. And this visualization here is used, this is similar to like Design Explorer, developed by Thornton Tomasetti, but this is kind of their new version called Thread. So probably used to seeing kind of one of these visualizations. So if we focus in a little bit more on those 3 visualizations, what we're actually looking at on the far left is MRT. So each one of those cells is showing the MRT value. And outlined in kind of the bold black line is all the values that are below our threshold, in this case 66 degrees Fahrenheit. The middle one is downdraft, and the same, we are outlining the areas that fall below 0.11 meters per second. And you can see the grid's a little bit lower, so that's ankle height. And then on the far right, we have our kind of combined thermal comfort metric, the PPD, the percent of the people dissatisfied. And we want to stay below 20% in this case is what our kind of agreed upon threshold. And all the other assumptions that go into this model, you can see highlighted there. Our R value, we assumed is a pretty low R value. This is to take into account, labor practices that may result in, R values that aren't necessarily equal to what we designed and what our like rated R value might be. So we're trying to build a very, very conservative case. And this was under the guidance of our engineers because, their names might be the one on the line when it comes to taking out radiant perimeter radiant systems and getting then the client coming back and finding that, faculty are complaining that it's too cold by the windows. So, in addition to that very conservative case is that outdoor temperature. The -5 degrees Fahrenheit, I think, is like the 0.1% coldest hour or temperature in the Pittsburgh climate, but it's happened recently and it's fresh in the client's mind, so they wanted to simulate this. So I'll cycle through a few iterations here. So we started off, I think the result of the 2000 simulations is that the vertical justified window all the way to one side was the best design. And that's most likely because, as you can see with downdraft, it's not necessarily kind of perpendicular to the window, it splays out a little bit. And same with MRT is that it's kind of accounting for your view of all the surfaces around you. So when you justify those all the way to one side, you're essentially killing, half of that effect. So you're able to kind of optimize or kind of take advantage of half the room that doesn't experience the negative effects of MRT and downdraft. So starting with a 4-foot wide window, we've then decreased to 3. So you can see maybe tiny bit of effect there. And the next kind of the largest effect here is to take into account a sill. So this involved us hacking Honeybee and kind of taking the findings from the literature and applying those to the values that Honeybee uses to predict downdraft and MRT. So we're just shortening the window to add a kind of a 3-foot sill there. And I'll just go back once more. So you could see on the far right, we have MRT values around 61. The downdraft right at the windows at 0.4. And you can see the PPD values are as great as 46. So when we go forward and add that sill, our MRT goes up to around 65. We're decreasing the cold area, the amount of cold surface area that we're seeing in our MRT. So our MRT increases. Our downdraft did not change very much because this is a product of the window height. So just by moving up the base, we're not adding a sill quite yet. I don't think, actually I may have mislabeled this because we're not actually decreasing the speed of the floor yet. And then we add, there may have been some confusion here in the slides, my apologies, but now we add the sill and the decreased internal heat gain. So we're going from like that lab heat gain down to our office. And you can see the profound effect that has. Kind of the combined PPD value now allows for roughly like 3/4 or more of the room to be considered comfortable. So this being our kind of best case that we could build, it's somewhat easy for us to make an argument that, a desk can be on the opposite side of the room, or it can be on the same side as the window, but maybe pushed back 4 feet from the window. So you're not necessarily right up against it where you may feel the negative downdraft effects. So second to last slide, I'll just kind of call out and acknowledge Payette did a really cool study, kind of one of these in-house rough and dirty mock-ups where they tested the effect of a double pane, traditional double pane, a double pane with a room side low E and a triple pane glass. They put it in one of these lab commercial grade freezers and dropped the temperature and looked at both the kind of the surface temperature, the kind of MRT globe temperature, which are stand-ins then for the downdraft effect and radiant heat loss. And if you look at this chart on the right, you can see the standard double, the surface temperature is around like 76, 77. With the double pane room side low E, it's actually lower. That's because it's reflecting more of that long wave radiation back into the space, so that surface temperature gets a little cooler. And by in a result of that, the downdraft should get a little bit cooler. As you can see, downdraft close is cooler than the double pane. But if you can afford it, let's go triple pane, and everything's better in that case. But that's kind of one of the great questions, because if I may not have explicitly said this, downdraft is, and MRT are mostly caused by the surface temperature and the amount of area that that window is taking up. So if you were to go triple pane, you can go a really long way to reducing the surface temperature of that glass. So in summary, I'll kind of like close with these kind of large questions that we can discuss, or you can think about who should be doing this analysis. I think individuals that are familiar with Ladybug tools, Honeybee, Grasshopper, can be doing this, but they should never be doing it alone or in isolation. They need to be consulting engineers and making sure that there's buy-in across the team, that if we can make this case and you can kind of set the conditions that we feel comfortable achieving through design, we can go forward and make get rid of those systems and save the energy, the cost, and the carbon. Obviously, Honeybee, I think, is one tool. Payet has another tool that's very similar to the Honeybee equations. It was developed by the same person. So if you were to use that, it's on their website. I would also say proceed with caution, knowing the limitations of that tool. The right time for this, as early as possible. If you can get, because if you're targeting removal or elimination of these perimeter systems, it's directly shaping your fenestration design. So these things are going to be tied. So don't go designing the facade and kind of backtracking and trying to figure out how to get rid of these systems. But I think largely, and this is kind of an outstanding question for me, is how do we understand the total trade-off between the highest performing glass, a triple pane that may eliminate those needs for systems and help dispel downdraft and MRT, and radiant and perimeter radiant heating. What I mean by that is like the total cost of those two things. Yes, we're paying for extra heating and extra systems, but triple pane glass is not cheap. And with that comes extra structure. There's a lot of other kind of compounding items that need to come with that. So I would advise, if you're trying to make this case, working with all those factors. Don't just look for, triple pane can drop our U value and our surface temperature, and that solves the problem. We know there's going to be a cost argument for that as well. But in doing that, you could try and price out the cost of a radiant system and see if that competes with triple pane glazing. All right, so that's it for me. I'll turn it back over and answer any questions if there are any.
Thanks, Kit. So yeah, this is the right time to ask any questions. We did have one that came into the chat box, so I'll go over that just so that we have it in the recording. There was a question about what tool was used by Apoorv and how everything was calculated. So Apoorv responded that in the project that he showed, they used Ladybug and Honeybee as well to calculate the operative temperatures and air, the ACH, with different window sizes and openings. And for them, the right size of the window opening was that can minimize discomfort hours based on adaptive comfort. So they use adaptive comfort as the metrics for that, and kind of use the same process that Kit just walked through, iterating through different opening sizes to calculate how many hours were comfortable versus uncomfortable. So any other questions? You can unmute yourself and ask it if you're not at a computer.
I think Jonathan has a great question about climate change.
Okay. So a question from Jonathan is, can you discuss further how climate change may affect your analysis? Thoughts about changing temperature ranges, climate conditions over time? Jonathan, who's that question for? Or is it just open-ended for any of the presenters?
Sorry, anyone, it's open for anyone. I think actually all three of the speakers might have something intriguing, but whoever's interested.
You go to Tommaso? Yeah, you can start.
Okay, very quickly. I think, first of all, the first question is, what is that climate data set that you want to use to design the building? And we often design or try to understand already what is the comfort projected in 2050. So I have some projects where we are doing this kind of analysis with projected data in 2050. And then it goes down to the client to kind of understand what is the risk that they wanna take in terms of, do they wanna install additional cooling capacity today, or, which is my position, do you wanna design today in a way that you have an infrastructure and enough flexibility that you can kind of future-proof your building and add additional cooling capacity in the future, depending on what is going to happen in the future. This is kind of how do we build today in a way that we can react tomorrow. So we think already that tomorrow we could need more cooling capacity, for example. And resiliency is also the other point. Whenever there is natural ventilation, use of thermal mass, this goes against some unpredicted scenarios in the future, and where resiliency and adding natural means are definitely a way to design against climate change in a way.
Yeah, that's a good answer. Yeah, I think very similarly, we will use kind of future climate files that predict different climate change effects in different regions to try and predict temperatures for the future. I think kind of an interesting provocation about how this folds into thermal comfort is that as we see more buildings brought online and warmer temperatures and seeing the grid overwhelmed, we're going to have to start to think about how to address those peak moments. And one typical demand response measure is thinking about drifting set points and seeing if we can coast through afternoons at a higher temperature, so we're not actually using cooling systems during those times. There's obviously financial benefits in the demand response, like financial structure for some regions of the country, but it's kind of interesting to have these discussions with clients to see, their willingness to go beyond a traditional comfort zone to either save money or doing it for the right reasons to not overwhelm the grid. And that, I think, is an interesting moment where we start to tackle what are low energy ways that we can keep people cool. And like fan movements, such as the one that was employed on the rec facility, is a really great one that is is useful at our desks. And I think we've all had experiences with fans too.
So a follow-up to that, Kit, Bunny asked a question like, how do you actually help clients understand the sense of risk when you're proposing something non-traditional? So what is the most effective way to persuade them to take the risk and do something new? Any tips, guys?
Risk management. So being very transparent about risks and not be scared about risk. Every time there is an innovation, there is risks. That's the definition of innovation. But you need to we cannot do innovation being naive. We have to be aware that, something can go wrong, and then the client needs to be aware that we have a backup plan or a risk management plan where we do mock-ups, for example, when we do computational fluid dynamic studies, where we know what can go wrong, and we have a design process to reduce the risks at the minimum, as when you do an investment and you choose high risk, low risk, and you need to be aware of what is happening. And when everything is clear, then clients, they can make their own decision. But what I always say is that when you put the client in the position of doing an educated decision, then you did your great job. And then at the end, the clients need to decide.
And I think, Tommaso, what you mentioned in the previous comment as well, flexibility, right? That if you can build in enough flexibility about potential, cooling for that matter, or any of set points and things like those, that you have the flexibility of changing the system or making sure that it's not going to be uncomfortable or anything, that I think that definitely goes a longer way.
Yeah, and I think this may seem idealistic, but I think maybe trying to pivot from risk to getting the client excited to try something new as well. I think if the playbook, I was probably just doing your homework, working with the design team to build a really compelling case that the client will trust and believe. And if you can make this the case that it saves money, saves energy, improves comfort, and there may be some recognition for doing something bold, I think it's something that individuals can get excited by. But it definitely depends on clients. And I think it's situational because some clients may have been burned in the past with taking a risk, and some may be, very interested in making a case and being like a precedent or a trendsetter as well.
Awesome. So Paul Mock is asking, for this heating season, was dehumidification considered with air movement? Paul, is this a question for Kit or one of the other presenters? And I'm assuming it's for Kit because he talked about a heating system.
Dehumidification considered with air movement. As like a way to improve comfort. I guess I don't completely understand the question. I think for heating season, usually humidity is pretty low. I don't think we needed any supplemental dehumidification. Air movement was, additional air movement, I'd say was kept at a minimum. We're kind of assuming that people are usually in like a cold thermal state, so they don't look at any additional air movement, but we did assume a background air movement just from ventilation of like 0.1 meters per second. If that doesn't answer your question, please elaborate in the chat or chime in.
Yeah. Okay. All right, awesome. So we just got one more last question in here. So Helia is asking how you think wearing masks in buildings might impact comfort and energy consumption, and how we can consider that in the occupant comfort and building energy performance analysis process.
Is there a CLO value for a mask? I don't know if that exists yet.
Good recommendation for Ashley.
Yeah.
Yeah, new emerging sciences. Okay.
I think it's a tricky one to answer. Yeah.
I don't see any. Well, first of all, we don't need to wear masks in buildings soon, I hope. I mean, now we do, but I'm always a bit. We should not. My biggest lesson learned through the pandemic, which we knew already, because that's the way we design, is that natural ventilation air quality is essential, and so that is the point. But we should not start designing buildings pandemic proof, because this is a kind of a peak situation which we should not design for, but react to in a way. So I don't see that much of an impact in between mask and energy. Comfort, absolutely yes, and it's exactly the point that comfort is so many things, right? The way you breathe to the mask, which is much more, have much more pressure drops to the mask. That's the point. Can make you feel much more uncomfortable within a space. So that is the only connection that I see, and hopefully we won't have to do it for long.
Okay, awesome. We are closing in on time, but we have, looks like there's a bunch of questions coming in. Should we go through them, or how are the presenters feeling? Do you have 5 more minutes to give? Mm-hmm. Yep. Yes, no? Okay. All right. So there's, all right, Dave, Josh had a question about, we often overcool and underheat based on the metrics. Any thoughts on what standard organizations to adjust to comfort metrics? I'm not sure what that question's asking, Josh, actually. Can you elaborate?
Sorry, yeah, I think this kind of builds on what Bunny's question was about, just kind of adjusting our ranges of comfort. And I think, Tommaso, you presented the different ASHRAE, the military, the different, the fitness organizations. How do we, and this kind of gets to how do we talk to clients about it, but how do we also talk to the respective, trade organizations to kind of get them to be more holistic in their approach as well. Just, it seems like they're focused on temperature so much.
I think ASHRAE Adaptive Comfort, which came in 2017, if I am right, did a big step ahead, and now I'm extremely happy about it. Following a dean being a German, then European regulation which was a bit ahead of that, and I'm pretty happy about it. Clients, especially in the North American market, they are still not used to it. And the point is that since it's a pretty recent regulation, there are not so many buildings in operation operated at these 26, 27, 28 Celsius with ceiling fans. So we are struggling a bit in finding new precedents, which is always tricky because, again, innovation cannot come with precedents, otherwise it's not innovation. So it's like a vicious cycle. It is also that what we recognized in post-occupancy, comfort is so personal that the more flexibility you build within a building, the better. So at the end of the day, having ceiling fans, having enough cooling capacity to range in between 25 up to 28, and then give the user the possibility of adjusting with decentralized systems and technologies, could be a compromise to say, you know, that's what the code says. The code says now ASHRAE goes up to 28, but then you can play within a range of 26, 28, depending on what you do. That is a bit my position there.
Okay, awesome. All right. Last question here. We found, it's from Richard Winston, we found that for a smaller building in humid environment, that a dehumidification system substantially reduced the need for cooling and therefore saved energy. Oh, it's actually a comment. I think Kit would probably agree or disagree maybe with our climate here in Philadelphia with KT's experiment with the dehumidification.
Yeah. That did remind me of that. I would advocate for like elevated air movement through fans as kind of being one of the best ways to really cut the effects of humidity. I think there's a certain point. You know, I think in our experiment at Kieran Timberlake's building, we got up to around 83 degrees Fahrenheit with a lot of air movement though, to still maintain comfort. And we had a flexible dress code. You know, I think there's a lot of measures that you know, we wouldn't expect all organizations to adopt, but this is kind of another case about risk management of like, if you can demonstrate through thermal comfort models that if everyone has a desk fan that blowing on their face, they can be comfortable at a higher temperature, you could effectively lower your cooling set point, save energy, save on peak loads. But with that comes maybe risk in terms of keeping people comfortable and, you know, people management on the client side too, expecting everyone's to kind of buy into that.
Okay. Well, thank you guys. The questions were really great and the conversation has been awesome, but I am going to quickly go over the tools for mapping thermal comfort. I know this is something that people are probably really interested in. So we did mention 2 of the projects we're using, Ladybug and Honeybee, to do a lot of their analysis, but there are other tools. Kit mentioned the glazing and winter comfort tool that Payette developed, that's free and available on their website. And then the CBE has 2 tools that you can use. There's the CBE Spatial Thermal Comfort tool, which doesn't use, which you don't need Grasshopper or Ladybug to understand, but you do have to get surface temperatures in order for this to calculate correctly. So you would have to work with your energy modeler or someone if you want to, as an architect, do this, to get surface temperatures to put into this tool. And then there's the CBE Set Point Savings Calculator, which basically it's an online tool that you can just put in how many degrees you're changing the set point by to understand what your savings are. It's a quick and easy calculator online that you can use to understand that. So those are design tools for understanding thermal comfort. And then there are post-occupancy tools. We'll mention Roast or highlight Roast here, which was developed by Kieran Timberlake, where you can use this in a building that's already established to understand how comfortable your occupants are after it's said and done. And so lastly, some key takeaways to take for this session is start with an understanding of climate and outdoor comfort first. That's what we saw in Apoorv's example. And you can also watch our session on bioclimatic design to understand more about understanding your outdoor comfort and climate conditions. And then there are more than 6 factors that contribute to thermal comfort, and each factor has its own series of factors dictating conditions at a given time and space. So, and then adaptive comfort with natural ventilation provides a pathway towards an expanded definition of thermal comfort, right? So how can you bring outdoor comfort indoors without using a system? And maybe a ceiling fan is all you really need. And lastly, think about the box and maybe outside of it too, to understand the spatially explicit nature of a thermal comfort. What architects design matters just as much as the systems plugged into a space, right? So ASHRAE 55 calculations are intended to prove a system can provide a set of conditions, but what about the envelope? So that's what we saw in Kit's example project, where the envelope starts to become part of those calculations way early in design. And lastly, we do have our monthly meeting third Thursday in May for the AIA COTE committee. We are looking for members. Join us. Mondays we do 2030 commitment. Tuesday there's policy and advocacy. Wednesday's environmental justice. Friday zero waste, and Thursday's design awards. So email any one of us and we'll get you all the links that you need. Subscribe to our calendar, etc. And that's it. Thank you very much, everyone. And have a great evening.
Thank you.
Thank you.
Thank you.
Thanks a lot.
Thanks.
Have a good evening, everybody. Bye-bye.
Bye.